Okay, now we're going to try the exercises. So, yeah, we discussed the theory. You can refer to that and all the stuff before that. Okay, first one is usually easy. So let's see. Y is a subspace of X. X has a topology. A is a subset of Y. Yeah. Then the topology A inherits as a subspace of Y is the same as the topology it inherits as a subspace of X. Okay, that's pretty simple. Let's see. So the topology it inherits as a subspace of Y. Let's call that the Y. What's that? What are the open sets? The open sets are going to be A, U open and Y intersection A, right? Okay. And tau X is equal to V intersection A. V is open in X. Okay. Y is not given to be, okay, nothing. Okay. Now, if U is open in Y and Y is a subspace of X, that means U is equal to V intersection Y. And V is open in X, right? Okay. So now what? Now, let's see. So U is open in Y, V is open in X, V is open in X. Yeah. Oh, yeah. Okay. And note that A is a subset of Y. So U intersection A is the same as V intersection. Note that because A is a subset of Y. So everything that's going to be in Y is in A is automatically going to be in Y. So we don't really need the intersection Y here for the intersection in case. And precisely because of that, these sets are the same. Yeah. Okay, next one. Okay, we have two topologies. One is strictly finite. What about the corresponding subspace? That's pretty simple. So tau prime is finer than tau, right? And yeah, so we have the topologies y gets from x, right? Okay. So essentially, it's going to be u intersection x or u prime intersection x, and these belong to the corresponding topologies, essentially, right? Okay. Now we're given that if you any yeah, so essentially every member is going to, so it's clear that this is the case because every u is by definition here, so every intersection is also there. Also, I just realized why. Yeah. So the corresponding tau prime topology is also going to be fine. That's the direct result of the definition. Okay. Yeah. What consider the set -1, 1 as a subspace of R, which of the following sets are open in Y, which are open in R? Okay. Yeah, that's pretty simple. It's just testing your knowledge of the definition. So the first is open in both, right? Oh wait, it's modulus. Oh, that changes some things. Not too many, but yeah, okay. Okay, so I'll just write it down. Mm-hmm. And yeah, okay. Now the first one is essentially minus 2 to minus 1 and plus half, so minus half 2 plus 1 minus 1 and plus half 2 plus 1. And note that these are the union of two open intervals. Also note that the open intervals in the order topology, or however you want to look at it, they're the same in the standard topology. That's how it's defined. So yeah, we have two open sets and their union is going to be open. So this is open in -1, 1, the subspace as well as the main topology, because it's not really altered in any way. It's still an open interval, right? Yeah. Note that -1 to 1 is convex. So the subspace and the order topologies are going to be the same. Okay. For this one, if we include minus one here, it's going to be open in minus one to one because it's essentially of the an open set of the third kind and second and third kind. So they're open, but they're not open enough because this is not open. And this is not even an arbitrary union because let's see. Actually, I never bothered proving why. Okay, actually, this can be shown why it's not open because essentially there cannot be a single set that. Yeah, we've done this theory essentially. Uh, the basis is finer, and that finer property is not holding, so it's not fine. So yeah, that's how you show it. Okay. The other one, open here, and closed here, is not open in either, right? It's not open in either because it's not even open in minus one, comma one, and the other one is the same. Yeah. In fact, if it's not open here, then it won't be open in R no matter. Can we guarantee that? Yeah, I think we can guarantee. Yeah. Hmm. Okay. For D, yeah, not open in either. Same thing. And for E, we have modulus between 1 and 0, and 1 by x is not the integers. Let's see. I'll just write it. I'll just make a picture. So the entirety of minus 1 to 0 is included here, right? And what about, so is 0 included here? 0 is not included here. Okay. Yeah. And then we have, I guess, 1 by 2 comma 1, and then union 1 by n comma 1 by n plus 1 essentially. Is that it? That should make the entire set, right? This is for all n. So essentially, it's if you want, you can make it this way. Yeah, yeah. So this you can, as you can see, is an arbitrary union of open sets. So it's open in R and in minus one to one because they're also open sets. They're all open sets in minus one. It's an application of exercise, the first part, A, the A in this question. So yeah, that's all question three. Okay, question four. A map is an open map if for every open set U. Oh yeah, I just discussed open maps, right? So I mentioned it earlier itself. And I actually, oh, I already proved why they're open maps. I'm not going to say. Okay, thanks. Yeah, okay. So we have x and x prime with their topologies. We have y and y prime with their topologies. And we want to show that x cross y is, which is final again? Yeah, tau prime is finer than tau, and mu prime is finer than mu, right? We have no idea what would happen if it splits figures. It doesn't make sense. Yeah, like not the set, this is the topology. Okay. So yeah, you just let's see, just take an arbitrary u cross v here, right? U is an open set in tau, and therefore an open set in tau prime. V is an open set in mu, and therefore an open set in mu prime, and therefore it lies here. So yeah, done. Now, what about the converse? The converse is, yeah, I'm not sure if the converse holds in the general product topology, which we'll discuss, but here it should hold. So let's see. Yeah. So you take any arbitrary open set here, U cross V. Yeah. So essentially, yeah, to show that tau prime is finer than tau, assuming this is the case. we just fix the topology, the open set on the other side. So let's consider all the open sets of the form U cross Y, right? So we can take a subset because of the axiom of comprehension if you want to get into it, but essentially, yeah, you can take all subsets where you fix the Y and then you consider only the variation here. And what else? Now, now what? Now, here, all of these are in both essentially, right? So it's already in here and yeah. Okay. So yeah. So every open set of X is going to also be an open set in X prime by definition here. And by X prime, I mean tau prime. It's going to be a member of tau prime. So are we done here? Hmm. Yeah, every open set of X is going to be an open set of X. That's exactly what we get. Uh, or if you want another way, suppose it's not, suppose there exists an open set that's not the case, then we can show that it's not finite. So that also works. And yeah, through a similar argument, you can show this. So the converse does hold here. I am not sure if the converse holds in generality or not. I'll think about it. Yeah. Okay. So yeah, the converse holds. Question 5 is done. Yeah. Either these exercises are more simple or the theory portion is just for some reason getting heavier than the exercises, which is not something I like. Anyways, question 6. Show that this is a rational another basis. Yeah. Okay. So we showed that by density A and B being rational is a basis for the standard topology of R by the density of the rational numbers, because we can always find two rational numbers in between two real numbers. Uh, I extended it formally, but yeah. So this is a basis for the standard topology of R, right? Okay. And now we just use the theorem. We want the basis for R cross R, but we already have a basis. So their product, the set of all their products essentially is going to be a basis for the product topology for R cross R. So that's the theorem, and we can directly use that here. And that's why this countable collection is a basis for R cross R. And you can prove it by induction for R. You have to, okay, so if we define R to the power n as R to the power n minus 1 cross R by induction, then we're completely fine. And yeah, then by induction is going to stay countable. But let's not get into that. Yeah, I think that's the last question now. Yeah, if L is a, oh no, hang on then. Yeah, let's go solve question 8. Yeah, let's go solve question 8. Okay, so we have R2, right? We essentially have R2 or whatever you want to call it. And we have boxes because we have products. Yeah, and okay, we don't have R2. We have RL, which is consisting of these open, not open, whatever, as bases, and then we have open intervals on the other side. So it's a product this way. So essentially, I'm going to write them down as this, right? And the line can pass through it in any way, or you can move the box around in any way. That's another way of looking at it. Yeah, so essentially we can move this box around, we can shrink it, we can do whatever we want with it and with it, and yeah, it can intersect the line in any way. And the point is, either we're going to get a clean cut with an open interval, or we're going to get a closed interval, right? So this line is essentially RL but rotated. Yeah. So that's the familiar topology. And here, if we take this case, so it's RL cross RL, we have a couple extra options, right? So we have this kind of closed interval as well on the line. And more importantly, we have this one. In fact, yeah, we just need this one and this one. So if we have all of these kind of intervals, what does that mean? Well, here's the thing. We can make this interval from this intersection, right? And we can make this interval from this intersection, right? So now that we've gotten both of these, well, let's see, B comma A and A comma B. And yeah, now what? Now, if you intersect them, you've gotten the singleton as an open set. And this singleton is arbitrary. So what does that mean? That means the topology that we get here is the discrete topology on this line. So yeah, it's familiar, but it's also boring. So you get the closed and the open interval in an order topology. Yeah, that's you can prove that. You will essentially get the discrete topology. So yeah. Okay. Did I do another one? No, I didn't. Okay. So to show that they're the same topology, I'm just going to show that they're both finite to each other. So let's see. So the basis element of RD cross R is going to be a singleton, some real number, cross an open interval, right? So essentially something like this. Okay, now what? Now this basis is obviously going to contain, well, the same thing essentially. A cross C, comma, A cross D. So this open interval in the dictionary order topology, mind you, is contained here, right? So what does that mean? That means the dictionary order topology is at least finer than this, right? That's one direction. Now for the other one, we take a base element, anything we want. Let's see, P cross C, uh, yeah, A cross B till C cross D, right? So this would be a base element in the dictionary order topology. Now we take any constant. Let's see. E is that's between A and C, right? And yeah, the exact same thing. So E cross B comma D. Is that it? Something's wrong. Yeah, cross B till C cross D, right? Yeah. Oh, we don't need B cross D here. Yeah. In fact, if it's in between them, so there are two cases here essentially. If A and C are equal, then we've gotten the exact same thing. If they're not equal, then yeah, the point is you can even take cross R here. It doesn't matter. You can take anything here. So because it is the whole line and essentially it goes here, 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 and then yeah, here goes, right? So you can take the entire line here. It's all fine. So yeah. But the point is, this is an open set in this product topology, and it's a subset of it, and it contains for right you had to consider for for an. So here it's identical, doesn't matter, but here you needed some element, so you can just take whatever you want, x plus y, and yeah. In fact, yeah, why don't you just take x cross whatever you want? If it happens to be A, then be careful. If it's C, then be careful. But otherwise, it can be the entirety of R. So yeah. So we just showed that they're both finite to each other through the basis theorem 13.23, and yeah. Okay, last one. I suspect the product topology is the finest one here. So let's see. Yeah. So let's say we have the ordered square here, and here's so this is not an open set in this is empty by the way. This is an open set in the product topology because it's a product of open intervals. Mind you, the open intervals include the open sets in this product topology include this type of interval. And so, yeah, by definition of product topology, this is an open set. Now, what's that? Yeah, a subspace topology, will this be open? Let's see. Yes, this is definitely open, but it is not open in the dictionary topology, I believe. Let's see. Yeah, because it has to consist of an open ray, and this is not an open interval, essentially. Yeah, I didn't mean open ray. I meant open ray. So essentially, between this and this point, it has to go through the lines and then come here, and this is not in the a part of the set. So the product, let's see, product, dictionary, and subspace, right? So this is definitely the case, right? Now we don't know about PNS here. Now the dictionary and subspace. Okay. Actually, yeah, the subspace is also finer here by definition this way. Okay, at least hang on. So what we've concluded is that dictionary order is not finer than product and subspace so far. That's all. So about the strictness, we don't know yet. So I guess, yeah. Okay. Now, any open interval, let's take this type of open interval. Yeah, the product topology would not have this as an open set. So I'm talking about the single line here, right? Why is that? That is because, well, yeah, the singleton is not an open set. That's the problem. So because of that, while this is an open set in the dictionary order topology, this is not open in the product or the subspace topology. So they're just straight up not comparable. Yeah, the dictionary topology is not comparable to either of them. Okay, now let's compare the product and the subspace topology then. So in general, they're equal. So is that going to happen here? Let's wait. What does that even mean? Hang on. Hmm. Okay, there is a little bit of a difference from this as included in the open interval. So let's check that out. Hmm. Yeah, I think they might be equal. Let's see. If they are equal, let's try proving that. Okay, so any open set and okay, so this was common for both of them, and that's essentially any square. That means the answer for the difference, if any, lies in the boundary. Hmm. Yeah. Okay. Oh wait, we might be able to game it. Right? So right. Okay. So in the subspace topology, we can get a closed interval here, right? Oh yeah, that's also part of it. Okay, that's bad. What about here? So essentially, yeah, we can get closed wherever we want, right? So closed here, closed along the boundary, in the subspace, we can get that, and in the product, we can also get that. Yeah, I suspect they're equal. Let's try proving that. So, okay, we take any basis element, so it can be of the form essentially open and yeah, open that and then intersect it. Mm, yeah, I think there's a direct correspondence. So whatever open interval intersection you take, or whatever normal open interval you take from the product topology of I cross I, you are going to get essentially the same thing. So they are represented by the same thing. You don't even need to find a finer, smaller number. Yeah. So if it's even if it's going to be closed here, yeah, and it makes sense. We did prove it. I don't know what I'm saying. So yeah. that solves it. And hopefully I do closed set soon. Soon. Yeah, my throat's not good or something. My tongue's tired, I guess. I have been speaking for 2.5 hours or something now. So yeah. All right then.